So, we are diving into something truly wild today. Welcome to The Explainer. If you follow the AI space, you already know things are moving at breakneck speed, but right now, there's a fascinating mystery unfolding right at the bleeding edge of the tech. You've probably wondered at some point, what actually happens when artificial intelligence agents start talking to each other behind closed doors? Well, we are about to unpack a brand new, absolutely massive research paper that tracks exactly that. It's a deep dive into the hidden mechanics of AI systems, and honestly, the results are going to completely upend what you might expect. Okay, let's dive into this. What happens when AI agents talk to each other? It's a question that taps right into a very modern and very intuitive fear. We all know that a single AI can sometimes hallucinate, right? It can just confidently make up facts. So the logical assumption is that if you chain multiple AI agents together, passing information sequentially from one to the next, those lies are just going to compound. You'd think they'd create this exponential spiral of errors, basically a high-tech game of telephone where a tiny little mistake at the beginning snowballs into total nonsense by the end. But is that actually what happens in practice? Section 1. The multi-agent AI problem and chaining AI models. To set the stage here, developers today are increasingly wiring different AI models together. It's super common. One agent writes a draft, another reviews it, a third fact-checks it, and maybe a fourth summarizes the whole thing. This sequential handoff creates a totally new environment, something researchers are now calling the hallucination cascade. It's basically the dynamic process where factual errors evolve, propagate, or crucially, get corrected as they move through the chain. Now, to actually track this, researchers had to break down the AI's responses into what they call atomic claims, essentially minimal verifiable factual statements. Think of them as tiny building blocks of truth. They wanted to track exactly how a single atomic claim survives that turbulent journey from the very first agent all the way to the last. Section 2. Testing the AI cascade in a controlled study. So, to map a cascade like this out in the real world, researchers published this incredibly comprehensive archive study, building a custom multi-agent system just to observe the phenomenon under a microscope. And you have to appreciate the sheer scale of this. 1,250. That is the number of evaluated responses generated across 500 distinct cascade experiments. And they didn't just test one narrow topic. They spanned 10 highly distinct knowledge domains. To top it off, they used 3 completely heterogeneous LLMs just to see how entirely different architectures interact with one another. They meticulously scored every single atomic claim for factual inconsistency. They essentially put a GPS tracking device on AI hallucinations. Section 3. The attenuation effect and the surprising twist. Remember that intuitive fear of an exponential spiral of lies we were talking about earlier? Well, here is the first massive narrative twist of the research. The reality? It's attenuated hallucinations. The data actually shows that our expectation is completely backward. The researchers found that in a 3-agent chain, the overall hallucination score actually drops. It goes from 0.422 at the first agent down to 0.272 by the final agent. That gives us an amplification factor of 0.644. And since that number is below 1, it proves net attenuation. As the information passes down the line, the AI agents actually correct each other. It's fascinating. They act as these corrective filters, spotting unsupported claims from the previous agent and revising them on the fly. And the deeper the cascade goes, the stronger the suppression of errors becomes. Moving on to Section 4, the cost of correction and factual decay. But hold on, because here comes the double twist. This incredible self-correction, it comes with a major caveat. The best way to think about it is like a water filter. Passing data through multiple filters absolutely removes the toxic hallucinations. But as you squeeze that data through the filters over and over, you inevitably lose some of the water itself. The researchers discovered that while the hallucinations drop, the overall factual accuracy also decays, falling from 0.789 down to 0.769. So, the outputs become much safer, sure, but they also suffer from information loss and semantic drift. By the end, the final response has drifted noticeably further away from the rich, nuanced details of the very original prompt. Now, what's really interesting about this slide is the exact breakdown of those claim-level transitions. It shows us exactly how that metaphorical water is being lost. Look, it's obviously great news that 35.2% of hallucinations are successfully corrected, and another 19.4% are weakened, meaning they're made much less risky. But look closely at that 11.4% slice. Over 1/10 of the claims are just outright deleted. To lower their hallucination scores, the later agents in the chain often just play the coward. They just remove details entirely to play it safe. And they also overcorrect 3.8% of the time, taking a perfectly factual statement and distorting or completely removing it when they didn't even need to. Section 5, Models and Topics and Semantic Drift. Now, you've probably guessed that not all AIs are created equal when it comes to surviving this cascade. What we're really looking at here is a stark reliability-efficiency trade-off across the different models they tested. Take Llama 370B, for example. It is the absolute safest model they tested, boasting the lowest hallucination score of 0.272. But it is heavy, taking over 15 seconds to respond. On the total opposite end of the spectrum, GPT 5.3 is nearly 3 times faster, clocking in at just 5.24 seconds, and costs half as much to run. But the catch? It hallucinates the most, with a score of 0.417. DeepSeek V3 kinda sits right there in the middle. So as a developer, you have a really stark choice. Do you want speed and efficiency, or meticulous reliability?
But the researchers actually found a brilliant engineering trick. Since they're chaining these models together anyway, it turns out the exact order matters immensely. The optimal cascade order they discovered basically starts fast and ends safe. You use GPT 5.3 as Agent 1 to rapidly generate the initial structure and get things moving. Then you pass that output over to DeepSeek V3 for a balanced refinement. And finally, you bring in Llama 370B as Agent 3 to act as the ultimate, strict, factual filter. This highly specific sequence actually achieved the absolute lowest final hallucination score in the entire study, dropping it to a rock-solid, highly reliable 0.263.
And this brilliantly illustrates that it's not just about the model you choose, the topic itself dictates the risk level. The hallucination rates actually swing wildly based on the domain being discussed. Grounded, well-documented science topics like photosynthesis and DNA, they survive the telephone game beautifully, maintaining super low scores right around 0.26. But the moment you ask the AI to synthesize broad historical contexts, like the Roman Empire, or highly abstract theories like black holes, the semantic drift becomes severe. The hallucination rates nearly double in those cases, pushing way up towards 0.48. Section 6. Building Better AI and the Whack-a-Mole Game. So, what does this all mean for the future of AI engineering? Basically, developers are left navigating this classic whack-a-mole trade-off. You absolutely can engineer out the lies by passing data through a deep multi-agent cascade. The data proves it works. But you will pay for it. First off, you're paying for it in increased latency and computational cost. Things get slower and more expensive. And secondly, you simply have to accept factual compression. By constantly suppressing the hallucinations, the AI plays it increasingly safe, stripping away the original prompt's rich, nuanced meaning. Ultimately, it leaves behind only the most unassailable, generalized facts. Which leaves us pondering this final, truly provocative thought. As we continue to build deeper chains and stricter filters to eradicate every possible error, we really have to ask ourselves, is a perfectly safe AI simply an AI that says nothing at all? Finding that ultimate balance between absolute factual reliability on one hand and rich, expressive creativity on the other is going to be the defining challenge for the next generation of artificial intelligence. Thank you so much for joining me for this explainer, and as always, keep questioning the algorithms around you.